So the 3 lectures are not today. No, that's okay. Don't panic. There will be 2 tomorrow. So good evening, everybody. I'm glad you're back here. So I will give you, as Matthew said, 3 lectures on optical lattices. I made some choices because I can make 5 lectures on optical lattices. Well, you always have to make some choices. So I will more or less follow this outline. I don't know exactly when will be the limit between 1, 2, and 2 and 3. It's not necessarily that today will be 1 and tomorrow we'll stop when it will be time. So I will introduce a little bit the topic today. That's not written there, but I will first give you some review on diffraction from optical lattices, which is a little bit different topic. I'm not sure I switched on the, is it on? Because
we can see that it's
okay. Last year, okay. So this is not on the outline, but I will start with that. And the plan for today is essentially to review once again for most of them, I guess, Bloch theorem and the band structure in a periodic potential. Tomorrow we will look at what's happening in the lattice when we speak of dynamics. Essentially, 2 things: what's happening when we switch off the lattice in different ways, and the second topic, which will be Bloch oscillations. And in the third lecture, I will go to strongly confining lattices, so time-binding limits, and the goal will be to establish the Bose-Hubbard Hamiltonian and discuss the mode transition. Okay, so first a few words. It will be pretty much connected to what Philippe already told you on optical lattices. And so, first thing, how do we make optical lattices? Well, we use standing waves. So you have a first plane wave coming from this side. Let's call it some amplitude and this phase. And the other one is just reversed in direction, such that the sum of the 2 will give some cosine kx for the field, and for the intensity, cosine squared kx, which is just like a 1 plus cos 2 kx, where k is a wave vector for the light, such that a period of such a standing wave is lambda over 2, where lambda is the wavelength of the light. So why does it make a trap or a potential for the atoms? Because you've seen with Philippe that there are, if you use far off resonant light, there is a dipole potential, which is proportional to the laser intensity. So some amplitude proportional to the max intensity. It is inversely proportional to the detuning. So I don't know. I don't use it really, so let me call it delta, but I will call everything V0 in a moment. And then the cosine, or 1 plus cosine, or so you can use either blue detuning or red detuning. It's for this kind of periodic lattices with the period lambda over 2, it's not very important. In other configurations, it may be very important if you choose blue or red detune light. But essentially, the idea is that this is a way you will create periodic potentials to trap the atoms. So the point that the period is lambda over 2 also means that the reciprocal period, which is 1 over or 2 pi over the period, is twice the wave vector, and this will be very important in terms of photon exchange and interpretation of momentum distribution in the lattice. So before we go to the dynamics in the lattice, band structure, etc., I would like to mention early experiments which were done by shining a lattice, a far-off resonant lattice, onto atoms, or in the other way around, to send an atomic beam through a standing wave and look for what's happening just after. So the standing wave is dephasing each atomic wave. There is no absorption, we are far off resonance, but still it's like a phase grating, and as a result, atoms are diffracted by this phase grating. So this view of introducing the optical lattices is the one which has led to experiments in the 80s already, using optical lattices to diffract an atomic beam. So as I said, the standing wave in this case plays the role of a phase mask, but there is no absorption, just a phase imprinting on the atoms. So there are two main regimes in which we can analyze the effect of the standing wave onto an atomic beam, or, well, I will use either one or the other point of view. Either there is an atomic beam going through a fixed standing wave, or we can also imagine that we have an atomic cloud and we pulse a standing wave on it and look for that diffraction on this cloud. So I will use either one or the other description, and in each time something important will be the interaction time, which will be either the duration of my pulse or the transit time for the beam through the laser, if it is a fixed laser and an atomic beam. So I will only consider what's happening along the x direction for the moment, x being the direction of the standing wave. So this direction, but do we still have the, yes. Okay, good.
1991.
Yeah, yeah.
Jesus, 1990.
1990, yes, but not 1991. I was pretty sure. I checked because I had a doubt. Okay. So I will first look at the regime, which is the thin grating approximation, thin grating regime. So the atoms, they go fast through the standing wave, or my pulse is short. So if the transit time, tau, which is typically the waste of the beam divided by the velocity of the atomic beam, is short, then the atoms, they don't have time to move inside. They don't have horizontal dynamics during the time they spend in the lattice. And you can imagine that you just have a phase imprinting of the potential onto the atomic wave function. And so if we start from some initial momentum state in this direction, what will happen is we just have for the wave function after the time tau phase imprinting proportional to the potential of the standing wave onto this initial state. So now the phase imprinting means I have to apply e to the I u tau divided by h bar. So u is this stuff. So it's an exponential of I square psi. But in fact, this guy, okay, I can first transform the sine square into some cosine, which is more regular. This guy I can expand onto regular plane waves. using an expansion in terms of Bessel functions. So this is just exact, they're infinite expansion. And now that I have written the potential under this form, this is just a translation in momentum space by an amount 2n h bar k. So the final state after crossing the standing wave is a combination with all these Bessel functions of my initial P0 minus 2n h bar k with a sum over n. So what this lattice does, it's giving kicks to the atomic wave functions in multiples of 2h bar k. And this is very easy to understand why. I have two standing waves like that, two beams like that. So the origin of the dipole force or the dipole potential is a redistribution of photons between the different components of the light field. So what is this redistribution? Well, the atom, they are able to scatter one photon from one beam and emit it into the other one. So if there is an absorption from this beam, there will be a kick in that direction. Now, if there is a stimulated emission into that beam, it will also give a kick into the same direction, and as a result, exchanging a photon from one side to the other one gives the atom a kick to h bar k. So there are photons exchanged, multiple of 2h bar k. And that's what we see here. And there is a weight, which is a Bessel function, telling you that you will not have any order, but the order is governed by the Bessel function. So here are two examples of this thin grating limit experiment. So the weight is the square of the Bessel function. First example, so the first one in 85, Pritchard and co-workers with sodium atoms, and the different pictures are taken by modifying the laser intensity or the velocity of the beam, such that if you modify laser intensity, you modify the coefficient V0, and if you modify the velocity, you modify the interaction time. So in either case, you modify the argument of the Bessel function, and for this reason, you also modify the weight in the diffraction orders. So it really nicely fits with the predictions. And the same kind of experiment was made 15 years later in the group of Anton Zeilinger in Vienna. It was very big stuff with very big molecules. C60, you know, it's this kind of football molecule. And nevertheless, it interferes really nicely because what's important there is center of mass, essentially. And so it's as if you throw a cat, more or less. Not as big as a cat, but you remove the hairs before. Okay, so this works quite nicely. So now there is another limit in which we can go. So I don't know if that's what I have in mind. I don't even remember what I have written there. Wait a minute. Okay. No, first consideration on energy conservation and energy changes. So what did change before and after if there is an exchange of 2h bar k photons? So you could wonder what's happening. So if I look into the x direction for the kinetic energy, I find that it has changed by 2 P0 h bar k over m, which is a recoil velocity, plus 4 times the recoil energy. So if the initial P0 is small because you come with a beam which is almost orthogonal to the lattice, so P0 will tell you that you have some angle, then it will be almost 4 times the recoil energy. So you may wonder, is it possible to diffract at all because you would like to conserve energy? But either in the pulsed configuration, you are allowed to not conserve energy if the pulse is very short, within some time, or you can also conserve energy in the in the situation where you have a beam crossing the grating, but in this case you are allowed to move a little bit the momentum along the z direction because the beam has some waist w, and for this reason not only along x you can have a momentum change, but also along this direction, or the transverse direction. There are also photons there which are a bit tilted because there is a waist, and so these photons can give you some small deviation which can ensure the energy conservation. So the maximum energy change, if I look in terms in energy change, so I go to the pulse direction description, along z would be given by saying that the initial momentum plus the momentum I can change along the direction of the beam must be on this order. So what is this momentum change? So this is very small, so I neglect the second order. I just keep the leading term, and it's h bar v, the m goes away, divided by the waist of the beam, and v, or the waist of the beam divided by v, is the time it spends inside the laser. So the energy change along z is on the order of h bar over tau, which is what I would also have for the tolerance I have on the energy change in a pulsed mode. So in either case, I have to compare h bar over tau and 4 irrec. So I will be able to observe these diffraction orders if tau is small enough such that this thing is larger than 4 irrec. Otherwise, it will not be possible to have a diffraction at all. Otherwise, I will have to conserve momentum and energy for this incoming beam with a imagine I come with normal incidence and I want to conserve energy and momentum. I cannot get a kick there or there, because otherwise it will have a larger energy after a kick if I'm not able to change p along the longitudinal direction. So for observing this diffractions order, I need to have this energy change along z larger than these 4 irrecs. So this gives me a condition for how short this pulse has to be, or how thin the grating has to be, and the condition is that the interaction time has to be small as compared to the recoil time. So now if I have a thick grating, much larger, or a long interaction time, so I said, no, I cannot observe diffraction orders. But it's not completely true, because I said that because I assumed I come orthogonal to the beam. But there are angles, if I choose them properly, which are able to satisfy both energy and momentum conservation. And this is Bragg diffraction. Indeed, imagine now I come with a beam which is tilted such that the momentum along the grating direction is minus h bar k. So now it's allowed for me to get a kick of 2 h bar k, because the momentum here will be p minus h bar k, or p ez minus h bar k ex, and the momentum here will be p ez plus h bar k ex, and the modulus of momentum is conserved, and the modulus of momentum is just the energy. It's p squared over m, so I have to conserve the modulus of momentum. And of course, the total momentum is conserved because I have the transfer from the photons to the atoms of 2h bar k. So this is possible. It is called Bragg diffraction. You have to come with a Bragg angle. It's just like when you use a grating in optics. And more than that, it's very nice because now you just have 2 levels which are coupled. You have the px equals to minus h bar k state, which is uniquely coupled to px equals to plus h bar k. So as you just have a 2-level system now, what you have when you cross the beam or when you pulse the beam on atoms is that you will couple two states of a two-level systems with a transverse coupling. So what do you expect that that happens if you couple between them just two levels of a two-level system? Question. It's written, not even able to read what is on my slides. So you expect Rabi oscillations to occur between the two p momenta. So if you have Rabi oscillations, it means that you can flip 100% the beam. So if you flip a beam, it's called a mirror. No? And if you stop halfway and make a half-half superposition, then you're able to make a beam splitter. You have half going through and half being reflected. And so with these diffraction gratings operated in the Bragg regime, you can build an atom interferometer, split with the first beam splitter with a pi/2 pulse, then use two mirrors using a pi pulse with the same grating if the atoms have not moved much or with separated beams, and close the interferometer with the last pi/2 beam and measure the population in the two outputs. So this is exactly the kind of configurations which are used in inertial sensors based on atom interferometry, typically gravimeters or gyrometers. They are exactly based on this scheme, and they use diffraction. So that said, I will not tell you more on diffractions with standing waves, because now we will consider rather the case where the light is always on and the dynamics when you have always this grating on, which I will now call an optical lattice. So the So the first experiments done in optical lattices where you don't have just one direction but several directions were the ones that Philippe mentioned this morning. That was very nice that you mentioned it this morning. In particular, the Raman spectra and the identifying the levels at the bottom. So this was done with near resonant gratings. So near resonant optical lattices. So near resonant, it doesn't mean it is on resonance. It can be even gigahertz detuned. But you expect that there are always photons scattered, and you even want them to be there to study the dynamics in the presence of photon scattering. So I will not describe this neither. I will assume that the detuning is very large, very large, very, very large as compared to gamma, and I will simply completely neglect light scattering. Okay? So I will not describe dissipative lattices because we have made a split between the two courses. You take the dissipative lattices, I take the conservative lattices. Okay. So now, how do we make these conservative lattices more than one-dimensional? Because I described the one-dimensional situation. So you could say, okay, that's very easy. That's like in a mod, you have one dimension and you copy, and you copy again, and now you have 3 dimensions. But you already had a flavor this morning that if you just do that, you will get into trouble, because you have to take care of the laser polarizations. So if you just have 2 beams here, I haven't written the polarization, but I assume that I had the same polarization for the 2 beams, say linear in this plane. Okay. Now if I have 4 beams, I can maybe add again, another beam pair with yet another polarization, but I will not be able to play this trick when I go to 3D, because I will not find some direction which is orthogonal to everybody. And anyway, already 2D, this is not quite stable configuration. So the regular trick that everybody's playing is to say, okay, anyway, look, my detuning is very, very large. So delta or delta plus epsilon, the result for the depth of the lattices will essentially be the same. I don't really care if I take this delta or another delta close to this one. It's not very important. So the trick is to use a frequency for this laser pair and another one for this laser pair, maybe just 60 megahertz away. So what will happen if you do that? You will still get interferences from all 4 or all 6 beams, but the annoying pattern you don't want to have from this interference, they oscillate at the frequency of 60 megahertz. So much faster than the atomic dynamics is able to follow. So basically for the atoms, all that averages to 0, and you can add independently the standing wave you had for direction x with the standing wave you have for direction y and the other standing wave for direction z. So at the end of the day, you are able to build a nice 3D square lattice like that, just overlapping 3 standing waves with slightly different frequencies. Okay, now you can also want to build more complicated configurations. And I will show you exactly the configuration discussed by Philippe this morning. So if you, I'm just looking what's happening in a plane. So 4 beams, so 2 standing waves and 4 beams with some dephasing between one of the field in the x direction and the field in the y direction. And depending on the choice of this phase, I can go if the phase is pi over 2, and then I consider the 2 lattices completely independent from the situation where I have the lambda over 2 period, just as if I had a different frequency. The situation is the same. To the situation where I have a lambda divided by square root of 2 period, I think, and yet another square lattice, but in a direction at 45 degrees and a different period. If I choose a phase 0, because this I can rewrite using x plus y and x minus y, and I can see that I have this kind of potential. And if I choose something in between, I can have a situation where there are different wells with different depth, and I can tune this in between and look for a more original configurations. So here the elementary cell, as you can notice, is not this small thing here, as in this case, but Philippe already mentioned that. So the elementary scale, or elementary cell, is something like that. So something tilted at 45 degrees. So what you can also do, if now you use a more complicated configuration, so if you superimpose 2 fields where one is a standing wave with some phase, and the other one is the result of 2 standing waves, but this time with a dephasing 0. So if you sum all those fields, that you can do something that you can do with superimposing essentially 4 beams. Then you can build a very interesting lattice configuration, which is called the brick wall lattice. And so how comes this is a brick wall? Well, look, here the connection between these 2 wells is not the same as this connection between those 2. So here are the bricks. If you look at the path for which the tunneling is larger between lattice sites, we have a shape which is kind of a brick wall, really. And if I deform a brick wall and I stretch it into that direction, it is topologically equivalent to an hexagonal lattice. An hexagonal lattice is what graphene is. And with this kind of lattice, you have very nice and interesting topological properties that I will not have time to discuss, but which are very important and relevant for quantum simulation nowadays. So all this to tell you that from now on I will describe very simple square lattices, most of the time 1D, just to describe the physics and understand deeply what we are doing. But experimentalists can build all a zoo of different lattices, also double wells, etc., by playing with the laser configurations.
Why don't you use previous at 120 degrees? Because you open immediately an hexagonal lattice.
Yes, so in the experiment of Tillman Esslinger, who developed this scheme, the answer is really trivial. Well, I don't have the optical access to access at 120 degrees, whereas I have nice optical access at crossing angles. So this was the way they still achieved this physics, even if they were not able. Yes, you're right. If you have all optical access you dream of, then yes, but very often you are limited to orthogonal optical accesses. So it's more a practical reason. Okay, so from this point on, I don't need the slide for a while. So let me switch this off. Okay, so I will give you lecture notes, probably tomorrow, because I want to add something which is not completely finished. There are also nice references you can find on optical lattices, which are in the lecture notes. And so for an introduction to the topic, you can go into the review paper of Emmanuel Bloch. I will show you a couple of pictures from this review written in the first issue of Nature Physics in 2005. And for the French-speaking students among you, there is a whole lecture series by Jean Dalibard at Collège de France, which is very nice, 2013. I encourage you to go there. And for those who are not French-speaking, but also for the French-speaking person, there are very good lecture notes written by Fabrice Gervier that you can just find by Googling. And about the dipole potential, but probably you already gave this reference, there is a very good review paper by Krem, Ovshinnikov, Weidermüller about optical dipole traps. You can find it on the archive. It's published in the Advances of Optical Molecular and Atomic Physics, but this is a book. Otherwise, you find it on the archive. So Krem, Weidermüller, Ovshinnikov, 99. This is in the lecture notes. So you will have the references. Okay. So now let's go to work. And the first thing we will use is Bloch theorem. So Bloch theorem, we will establish it and see how it's derived. States that if I have a Hamiltonian which is the kinetic energy plus some potential where V is periodic. Then the eigenfunctions, or the eigenstates if you prefer, are under a very nice form. They are labeled by some vector q, and they are the product of a periodic function, periodic with the same periodicity than the potential, times a plane wave with this q as a wave vector. So this is a Bloch theorem. And we will try to establish that. So first thing, we will introduce the translation operators. And in particular, the one which interests us most are the one which translate by exactly one of the periods of V of R. So the translation operators, so let me specify what is the periodicity of V. So V of R is such that V of R plus D is equal to V of R if D can be written as integral steps of the periods in the different directions. So there will be 3 directions which can generate the space if I am in 3D, otherwise it's 2, and in 1D it's just 1 period. So the ni's are integers, and the ai's, they define the elementary cell that I discussed by showing you the pictures before. So if it's difficult to make a drawing in 3D, so I will stick to 2D. So if I have A1 like that, for example, and A2 like this, then it means that I have a potential which is periodic with this kind of periodicity. So if I have a minimum here, I will have one here, and one here, and one here, and another one here, and here, and here, but also there, and there, etc. Oops. So this is the lattice, and that's why it's called a lattice, which is below the structure, which is below the periodicity of V. So in 3D, you just add one more direction. So the AIs are not necessarily orthogonal. For square lattices, as I have shown, the AIs form a basis, orthogonal and orthonormal basis. So they are all orthogonal, and they are the same length. But if it is a rectangular, then one of them is larger, for example. If it is a triangular, is different, etc. Okay, so this is the lattice in real space. And this lattice is called the Bravais lattice. So as in the Hamiltonian, I have p squared over 2m plus v, and v is periodic over this Bravais lattice. It means that the Hamiltonian H will commute with any translation operator along this Bravais lattice. So what are the translation operators? the translation operators in general, from a translation for any vector, let's say v, it's generated by the momentum operator. So this is a translation by some vector v. Such that if I apply this to some state psi, the wave function associated to this psi will give me psi of r minus v. Of course, as it is built on a momentum operator, T commutes with P. It's just a P operator in there. So the operator is only this guy here. Look, okay. So T, let me put hats to be specific. T commutes, any TV commutes with P. But in addition, as V is periodic on the Bravais lattice, V also commutes with all the translation operators from a translation from a quantity which belongs to the Bravais lattice. So if I call B all the D's, so all the N1, A1 plus N2, A2 plus N3, A3, where the ni's are in Z. So this is an ensemble of vectors. This is a Bravais lattice. So for any D in D, the whole Hamiltonian commutes with the translation by a vector D. This just tells you that V is periodic with any translation from an element of P. So it commutes with all the T, the smallest possible translations, the TAJs. Which has the one which generate the Bravais lattice. So a remark also, if I look for the inverse of the translation by D, well, the translation, if I look for the inverse of the translation by D, it is a translation by minus D. And the translation by minus D is also the Hermitian conjugate of the translation by D, because if you replace here D or V by minus D. So the inverse of the translation operator is equal to its Hermitian conjugate. So T dagger is equal to identity. It's a unit operator. So as it is a unit operator, it means that its eigenvalues are of unit norm. So they are of the form e to the I some angle. Okay, so if of course, if and in fact all the thetas can be chosen, but I have to limit theta into 0 pi, or if I choose theta plus 2 pi, it describes the same eigenvalue as theta. So I will write e to the minus a theta j, just to be sure, an eigenvalue, one of the eigenvalues of t a j along one of the generators of the Bravais lattice. Okay, so now it's time to introduce another lattice. Which is a reciprocal lattice. And this reciprocal lattice is the Bravais lattice generated by B1, B2, B3 which are such that if I take the scalar product of one of the A's by one of the B's, I find 2 pi delta ij. Okay, so it means that if I go back to my lattice, I need that the B1 is orthogonal to A1. The B1 is orthogonal to A2, sorry. So B1 is maybe something like that, with the right length to have the scalar product with A1 being 2 pi. And B2 is orthogonal to A1, so it can be there, for example. And here, if I take the scalar product with A2, it also has to be 2 pi, so at least it's in the same direction. So if I have a lattice like that, the reciprocal lattice is generated by two vectors like that. So it's not necessarily the same kind of lattice or angles than the original lattice. In my example, because A1 and A2 are not orthogonal, B1 and B2 are also not orthogonal, and they do not have the same angle between them. So this is called the reciprocal lattice. And now we will define Q, a vector of the reciprocal lattice, under the form, the sum over the j's of theta j bj. So the b's are the elements of the generators of the reciprocal lattice, and the theta is the one which gives us a specific eigenvalue of the TAJ operator. Now, if I take the scalar product of one of the A's by Q, as AI Bj is delta 2 pi delta ij, only the product with Bi will remain, and it will give 2 pi. It will give 2 pi, so it will remove the 2 pi, and what I find is that this is nothing but theta I. Such that the eigenvalue of TAI is in fact e to the minus I Q A, so I said J just to avoid the wrong eyes. So this is what the eigenvalue is. So now let me look at the eigenstate. Okay, something I forgot to say, and which is very important, is that as the Hamiltonian commutes with all the AJs, the T AJs, we will look for eigenvectors which are common eigenvectors of both the T AJs and H. That's why we wrote that. So my eigenvectors of H will also be eigenvectors of the T AJs. So the psi Q I'm looking for is an eigenstate of H and TAJs. So now if I look at what is the expression of psi q taken at a position r minus aj, with psi q the eigenstate of both h and taj. So this is nothing but the translation operator applied on psi q. And as psi q is an eigenvalue of Taj with an eigenvector of Taj with this eigenvalue, it is nothing but e to the minus iq dot aj psi q of r. So if I have this eigenstate I'm looking for, it verifies this relation. That if I look what is its value one step further in the lattice, it is the same as the previous value, but dephased by some coefficient, which depends on Q. So if I make one step in the lattice, I almost don't change anything, just the same psi, except that I have taken a phase shift of q e to the I q aj. So now why can we say that we have written the eigenstate under this form? Well, that's basically what is written there. Because if I take one step with one of the lattice period, this will not change this part. This u of q is periodic with the lattice. And this will give me a phase shift, which is e to the I q ai. So to formalize this a little bit more, I can, starting from that, I can define function u, q, which is just e to the minus I q r psi q of r. And if I wonder, is this function periodic? Because then I have wrong, because this is what I try to prove. But let me just write what is uq of r minus aj. So it's e, and here I have to put r minus aj, so eqr plus iq aj, and then that's psi q of r minus aj. But this guy, I've just said that it is e to the minus iq aj psi q of r. So this is nothing but psi q of r. And psi q of r times e to the minus iq r, by definition, is uq of r. Conclusion, indeed, we can write the eigenfunction of the problem under the form periodic function on the Bravais lattice times a phase proportional to QR. So this Q is defined this way, and what we've said is that this theta is defined modulo 2 pi. It's not useful to go further than minus pi plus pi, because if I take another step of 2 pi, I get the same eigenvalue for the translation operator, so it is the same state I am describing. So as theta has to be restricted between windows of 2 pi, it means that Q is restricted within a vector of the reciprocal lattice. Q is a sum over j of theta j divided by 2 pi bj. So imagine I look at q plus one of the b's, q plus bi, and then it will just be theta I plus 2 pi over 2 pi bi plus the j's different from I, theta j over 2 pi bj. And theta I plus 2 pi describes the same state and the same eigenvalue as theta. So I'm describing, at the end, I'm describing the same wave function. I'm describing the same eigenstate of the Hamiltonian and the T operators than what Q describes. So in fact, I can restrict, to get all the possible eigenstates, I can restrict Q to be within one of the cells, one of the elementary cells of the reciprocal lattice. It is enough to get all the eigenstates. So we can restrict our description to just one cell of the reciprocal lattice. So the cell which is, say, around 0, where you take a Q to be a lambda 1 B1 plus lambda 2 B2 plus lambda 3 B3, where the lambdas belong to minus 1/2, 1/2. So this one is called the first Brillouin zone. And I will usually use this notation. So this Q is a kind of parameter which gives you which eigenstate you are looking at. And this Q is called the quasi-momentum. It's quasi-momentum because it's not quite a momentum in the sense that Q and Q plus Bi describe the same state. So you cannot say for an atom it has a momentum and another momentum shifted by some quantity. So it's a quasi-momentum, and it labels all the states. When you go through this first Bill-1 zone, you will be able to find all the eigenstates of the Hamiltonian. And so once Q is fixed, to find the eigenstates, you have to look for the Hamiltonian problem, and you will find different states with different energies that you can label by an integer. And this is true for any value of Q. So once Q is fixed, when you look for the solution of the Hamiltonian, you will find a spectrum at this Q. And you choose another Q, you will find another spectrum at this Q. And by scanning all the Qs, you will find all possible states of the Hamiltonian. So the psi Qs are called the block functions, or Bloch functions, if you prefer. And the Q is a quasi-momentum. And the Bloch functions are the eigenstates of the Hamiltonian with the periodic potential. Okay. So these Bloch functions constitute a basis of the Hilbert space, in fact. So I have added a small label n, which is the n which I mentioned briefly. So for each Q, you have a spectrum of energies. E0 of Q, E1 of Q, E2 of Q, etc. So this little n is this index of the state for the given energy once Q is fixed. And so all the Bloch functions form a basis of the Hilbert space and satisfy an orthogonality relation. Okay, I will write it this way. So I will write it this way because it will be simpler for me to quantize the momentum in a box for most of what I will do. Yes.
Can we say that the reciprocal lattice is a Fourier transform of the real lattice? Or
The reciprocal lattice? But what is the Fourier transform of a lattice? Essentially, it's a yes, it is a lattice with 1 over yes, kind of, because it's a lattice with periods which are 1 over the lattice period, at least in a square lattice, of course, it works. Yes, I think so. Good question. Yes.
For Q, does it have a physical meaning or just mathematician meaning? I mean, when an atom placed in an optical lattice, and we want to
I
know
will
the
discuss
momentum,
that lengthy later. Okay. I
because
keep
the
your question
momentum-
for later. We will discuss a lot the physical meaning of the quasi-momentum. So, for the moment, it's a label. But in fact, it will play the role of momentum in lots of situations. So I will come back to that later. Okay. So what I'm saying here is that I will work in a box. So there Q and Q prime will be discrete indices. There are several choices I could make. I could look at an infinite system and work with integrals for Q. Then there are normalization problems which are boring. And so I decided instead, I changed several times in my lecture notes, and at the end I decided to work in a box because it's simpler to normalize properly everything. So I will work in a box of size L. So imagine these two lengths are the same, okay? And it means that the Q, they will also be quantized in a quantization volume 2 pi over L with the three directions of space. But this quantization is not linked to the fact that there is a lattice, okay? Because the box is very big. So the box is 100 meters per 100 meters per 100 meters, and my sample is a tiny piece with 100 micrometers size. So it just, you can imagine that L goes to infinity at the end of the day, such that this quantization is purely technical. And at the end, you can imagine Q as varying continuously. So it's not because there is a lattice somewhere and a strange quantization of Q. No, it's just technical mathematical reason that I prefer to work in a box. And in this case, you know that Q will be quantized. So box with periodic boundary conditions, Q will be written under this form. So L goes to infinity at the end of the day, okay? So that's why I am allowed to write that, because now the Q's, there are a finite number of them, and so I can have a discrete Kronecker symbol between two Q's. Okay, no problem with that. That's vector Q. Okay. Small remark. The problem is also invariant under the time reversing symmetry. Where you change t into minus t. And when you do that, you change the wave function into its conjugate. And p into minus p and r into r. So this gives another solution with the same energy. And for this reason, the energy associated to the quasi-momentum Q is the same as the energy associated to the quasi-momentum minus Q. And this we can prove by just replacing psi by a psi star, which will the psi star will change the Q in minus Q essentially, and you still have a periodic function, so you still have the same another Planck function with the same energy. So that's why the energy for state minus Q is the same as the energy with state Q, which is very practical because it means that with respect to the first Brillouin zone, in fact, you just have to explore eighths of it to get everything, because then you just make reflections and you get the other 7 other quadrants. So the spectrum is symmetric with respect to Q minus Q symmetry. Okay. What is it? Probably lecture 1 will continue a little bit tomorrow. Right, so let's look at these energies. And for that, we will start to restrict our description to one dimension, because it's much simpler. So we have just one dimension with the Hamiltonian, which now is just V of x. And what we want to look at is the spectrum. So for each, so imagine the period of V, I call it A. So it means that the reciprocal lattice, the little b of my reciprocal lattice, there is just one, so I don't have problems of having a bi dot aaj0. B is just 2 pi over a. So as I can restrict myself between 1/2 of b and plus half of b, it means that the first Brillouin zone is just the interval between minus pi over a and plus pi over a. And now, for any q in this first Brillouin zone, I will have a spectrum of energies, En of Q, eigenenergies corresponding to the eigenstates, which are the block vectors psi and Q of x. So the Q's, the psi and Q of x are, because of the block theorem, of the form e to the I qx, u and q of x, where u and q is periodic with the period a. So as it is a periodic function, I can write it with a Fourier decomposition, Fourier sum. So it's a sum over all possible values j's in z of some coefficient, which depends on q and on n, in fact, in principle. So I'm not sure I will keep the n always, because I'm a bit lazy. But okay. And e to the I j. The period is a, so it's 2 pi over the period times x. So this is just writing that u and q is a periodic function of a, and as it is a periodic function, I can expand it on the different harmonics multiple of the frequency 2 pi over a. And so to find to solve the problem, I can put the value of the block function under this decomposition inside the Hamiltonian problem and find what coefficients alpha j I have to put there for the eigen problem to have a solution with energy En of Q. So first remark I can make, as I can write the eigen function, this block vector, under this form, this is the X representation. Now I can also write psi under a P representation. And what I find is that this psi, if I look at what it is in the P representation, this is just the wave function associated to a pure plane wave with momentum h bar q plus j 2 pi h bar over a. So this is just a sum with coefficients alpha and j of a comb of momenta, so h over a if you prefer, or 2 pi h bar over a, where all of these states are pure momentum states with some well-defined momentum. So the block function is in fact a comb of momenta with equal spacing, with a spacing 2 pi over a. So now if I look for the solution of for the energy, I will have to inject these block functions into the eigenvalue problem. As this guy is just a comb of momenta, this p squared will be very simple because it will just be the momentum squared over 2m. And v will not modify it's just a product with the wave function. So at the end, if I look at what it gives, it will just give me p plus h bar k squared over 2m plus v of x u and q is equal to e u and q. So this is because psi is u times e to the iqx. So applying p squared onto psi is just like applying p plus h bar q squared on u. It is a translation of h bar q in momentum space. And so to find the solution, well, you find you look at this eigen problem for u for each given q as being a fixed level, and you find the eigen functions un for this given q and the energy. So in fact, normally you do it numerically, and the q is in the first Brillouin zone. Okay, so just to be consistent with my L, just to tell you how many Q's there are in the first Brillouin zone. So the first Brillouin zone is between minus pi over a excluded and pi over a. And the Q's, they are spaced by 2 pi over L So there are a number of states inside this interval, which is equal to n over a. L over a states in each for each n, little n. So there are L over a different values for Q, and for each Q you find the whole spectrum labeled from n equals to 0 to any n. Okay. So from now on, we will concentrate mostly on the specific case of a sinusoidal potential, because it's pretty much what you get when you have a standing wave. It's a very important example. So for the numerics, I will show you the different states and bands I have computed. I have taken a sinusoidal potential. So if the potential is sinusoidal, it simplifies a bit the Fourier decomposition of the periodic potential on the different Fourier frequency, because essentially there is just one frequency. So it will simplify a lot the description. So now I will use a specific case, which is a sinusoidal potential of the form sine squared kx, which does not come from anywhere, which comes from what you get when you interfere two beams. So when you have in mind the fact that it's optical lattices with two beams interfering, the k, which is here is the wave vector of one of the lasers. So the period, we know, I said it at the beginning, is half of lambda, such that the first Brillouin zone, which is minus pi over a and pi over a, I can also write it as being between minus k and plus k. And so here, if you remember what we've said at the beginning with the atomic diffraction, that we had the 2h bar k wave vector, which played a very important role. That's not for random. That this is minus k and plus k. It is completely linked to the fact that there are photon exchanges and that there are two h bar k kicks in the problem. And so, as we already commented, that the block function is a comm of momenta with different momentas split by 2 pi h bar over a. Now, if a is pi over k, what you see immediately here is that the momentum comm which is there is a comm of 2h bar k. So it's a comm with a splitting between the teeth of the comm of 2h bar k. So the potential I will write in such a way that we can immediately see what are the Fourier components. So I used a sine squared kx because that's what we get when we have a field which is just sine kx. And if I give the expression of sine squared, it will involve, of course, a cosine 2kx. That's why the period is lambda over 2. So I can write it with cosine 2kx, or I can also write it with the exponentials. And what is nice with this writing is that, again, I see clearly appearing the fact that this potential is a translation operator in momentum space of a quantity 2h bar k. So this is a translation by minus 2h bar k. This is a translation by plus 2h bar k. Or the other way around, I never remember. But this is why we have the possibility to get kicks in this lattice. So the lattice period I gave already, first Billouin zone, okay, and the important energy scale I will use from now on is the same as in the lectures of Philippe. As we have a momentum scale, which is essentially h bar k, the relevant energy scale is a recoil energy. So I hope we have the same definition of the recoil energy. Yes, good. And I will sometimes also use a recoil frequency, which is nothing but the recoil energy divided by h bar. Okay, so now I will take, I think, 15 more minutes, but you have plenty of time because you are not tired and not too hungry. Anyway, the restaurant opens only at 7:30, so nobody will complain. No? Some will complain. Okay, so now we have to solve our eigenstate problem, and I will start with a case which will be very easy, even trivial. And the trivial case is when V0 is 0. So it's a lattice with 0 amplitude. So in principle, you know the answer. When you just have p squared over 2m, you expect that the eigenstates are just momentum states. That's true. So in principle, the eigenstates are of this form. Well, they are of this form, not only in principle. But now we will write P in a funny way. So let me write P under the form h bar q plus j to h bar k, where j is an integer and q is in the first Brillouin zone. I can always do that. And in fact, the integer j is something like, or the q is something like the, so j is the integer part and q is the rest. I don't remember what's the name, fractional part, in Euclidean division by 2h bar k, okay? So not exactly, I have the offset because I want to center everything around minus k plus k and not around 0, but this is essentially Euclid division. So I can always write P like that, and there is just one way to do it, with Q being here. And so in this way, the e to the I p q h bar writes e to the I qx times e to the I j 2kx. Okay, I'm happy. This is Bloch theorem. This is my e to the iqx, and this is a periodic function with period lambda over 2. So it also works with 0 amplitude. It is still under the form of the Bloch theorem, even if it's quite simple there. And so what is the energy I can associate to this Q? Then the energy associated to the Q, but it's p squared over 2m, of course. So it's h bar squared over 2m Q plus j times 2k squared. So this would be, in fact, any of these. Now I have to decide what is the band in the problem, because my Q is just between minus k and plus k, and I would like to make a drawing where I have Q going just between minus k and plus k, and being able to have all the energies of the problem. So if I first take j equals to 0, I will have the lowest possible energies, which are just a parabolic potential, as you expect. And the spectrum for the free particle, it is just a parabola, okay? In principle, it continues like that. But then if I take the description in terms of Bloch functions, and I want to restrict myself to the first Brillouin zone, then the Q is only there. So if I have a j which is non-zero, for example, if j is 1, then I will have, for the same Q, say Q equals to 0, for example, I will have, if I take j equals to 1, an energy which is now 4 recoil energy. So if Q is 0 and j is 1, I have 4 recoil energies. So if Q is k and j is 0, this is 1 recoil energy, so this is recoil. And then 1, 2, 3, 4. I have a state there. The state which corresponds to Q equals to 0 and j is 1, or j is minus 1. And I have also a state which has the same energy than the one with j equals to 0 and Q is equal to plus k, which is a case where j is minus 1 and Q is equal to plus k. So in plus k, Q equals to plus k, I have two states, the one with j equals to 0, which has for energy the recoil energy, and the one with j equals to minus 1, because now I have k minus 2k, this is minus k squared, again I find the same energy. But then for j equals to minus 1, if I change Q, instead of staying at Q equals to plus k, now I decrease Q. As j is minus 1, I start from k, and when Q decreases, I have minus 2k plus Q, or minus 2k plus something smaller than Q, so minus 2k plus something smaller than Q. Or if you prefer, I reverse everything, so j is minus 1, it's just 2k minus Q squared, because it's a square. I can just reverse it. So when Q is k, it is k squared, but when Q decreases, it increases up to the 4 recoil. So here is this second energy band. And the same, of course, for this situation. And if I continue increasing, I will have something here which goes up to 9 recoil energy, etc. And this bit here, of course, is just the same as this part of the free particle spectrum shifted by 2 h bar k. And this bit here, this one, it's just the same as the free particle spectrum shifted by -2 h bar k. So finally, what you find in this case is that if you look inside the first Brillouin zone, you can still interpret the spectrum of a free particle in terms of bands. It is just that these bands are sections of parabola shifted in order to come back into the first Brillouin zone. So each time you go outside, you fold the parabola to get back inside the first Brillouin zone. So now this is for the case where there is absolutely no coupling, but now if V is non-zero, what it will do is that it will be able to couple these two states. So this state here corresponds to Q equals K and J equals to 0. So this one here. And this one is Q is equal to K and J is equal to -1. And they are degenerate here. But if we switch on the lattice, what the lattice is able to do, it is able to give 2 h bar k kicks. So it is able to change J, essentially, to change the momentum by 2 h bar k. So it is able to change J. So what it will do is that it will be able to couple those two states here, which were degenerate at this point. And as you know, in general, when you have a coupling between two degenerate states, it will open a gap at this position. So how do you find the eigenstates? Where you use the method I have described here. And it's easier when you have a potential which is just composed with two translation operators, because then you can simply get a series of equations labeled by the Fourier component you are looking at. And so in order to find the eigenstate, that's exactly what you do. I will not give much details, but if you write the wave function like that and you plug it into the Hamiltonian equation, what you find is that you have an equation for the coefficients. So this times alpha j of q minus v0 over 4 alpha j plus 1 of q minus v0 over 4 alpha j minus 1 of q is equal to 0. So how does that come from? Well, you have the Hamiltonian here. You write v0 under the form which is here. So you have something diagonal, which comes just as an offset in the energy. You are looking for the eigen energies, so the E also is diagonal in a sense. You can put it in front of the same Fourier coefficient. And what the V0 e to the I 2kx or minus I 2kx do is just shifting the index of your decomposition, because it will compensate for one of the j's. So now you have a relation between all the j's with alpha, which relates alpha j plus 1, alpha j minus 1, and alpha j. We go into numerics. You take enough j's to converge nicely, depending on the system you look at, and you find the eigenfunctions and eigenenergies. So why does it open a gap? If you look at what's happening close to the edge, you have the situation where you have a Q, which is, say, if we look at the right edge, Q, which is close to K. And so if you look at what's happening close to the edge, you will have locally the Hamiltonian. You can concentrate on the coupling between only these two states you have without coupling. As I said, so the energy for both is a recoil energy in the graph of free particles. Now you have this offset of V0 because of this term here. And if I write the Hamiltonian, I have these terms in the diagonal, which couple the state K plus 2, K plus 0 and K minus 2 h bar K. So in a sense, it couples plus and minus h bar K. And so this you know how to diagonalize. You just have an offset in energy, and the eigenstates will be just a combination of h bar K and plus minus h bar K in terms of real momenta. So if I look at P and not Q, okay. If I look at P, the two which have the same energies are P equals to plus h bar K and P equals to minus h bar K. And now they are coupled by V0. And the splitting in energy due to this coupling, if you look at the energies, you will find that the eigenenergies are the offset you had before, and then plus minus V0 over 4. So you find that there will be a splitting here occurring at this point if the lattice now is non-zero. And for a small coupling, this splitting here would be V0 over 2. Okay, so let me show you a little bit. Yes, it's time. Thank you. Some of these... oui, ça marche pas, si? T'as allumé? Ah, ok. Je sais pas si c'était plus rapide tout à l'heure. Ah, ok. Ah, si j'avais su. But that's a... It's on, but the screen does not come with it. Ok.
Il n'y a pas de bouton là-bas. Tu peux faire off si tu veux. Mais
ouais, mais bon, non, c'est peut-être pas la peine parce que ça va le bloquer. Interesting. So let's see what you see if I just put... Non, on voit rien du tout. Attends, c'est quoi ça? Ok, so okay. that the students that are too tyrant and that organize that I have to stop here.
Okay.
So I will show you the curve tomorrow because you can't see anything. And so let's continue tomorrow. Yes.
Is there, so basically when you use the standing wave, you have a lambda over 2 spacing for the.
Yes.
Yeah. So is there a way to get like
Lower, smaller.
Smaller lattices?
You can reduce lambda.
Okay.
And ah mais d'accord. You can what you can have is within a period when you use funny interferences, you can have, for example, a double well. So with the two wells separated by less than lambda, then or less than lambda over 2. Or otherwise you have to play tricks of internal state superposition and using dark states and EIT and stuff like that to create a very narrow structures. But nevertheless, for the period itself, I think you're more or less stuck to lambda over 2. You can do more, of course, but otherwise you need to go to nano-fabricated structures or things like that if you want to go to smaller periods.